Okay, everyone. I'd like to start a lecture on grids. The first thing I'd like to do is show you where in Blackboard you can go to see this information. If we go to Blackboard and PowerPoint/PDFs, you can scroll down and we are up to the lecture on controlling scatter in the remnant beam. So here is our lecture here. I want to point out that there is a second link, and this is information I found out on a website, but I looked through it and it's very good. You can start with slide 36, but the previous information to that is also good as well, and covers some of the things we talked about in our last lecture. So I'm going to go ahead and go to the PowerPoint through the Google Doc. And we'll click. Okay. So here we are. I'm just going to go into the presentation mode for this. All right. So scatter control in the remnant beam. If you take a look at these two images, not too hard to tell that the image on the left is really gray. I wouldn't even say low contrast. I would pretty much say bad contrast. So there's an awful lot of scatter that's causing this fog, whereas the image on the right, a lot of that scatter has been cleaned up. We're now able to see the contrast much better. It's still a long scale image, meaning that there are more grays, less black and white than what you might have in an extremity, for example, but it is vastly cleaned up in terms of scatter, and our contrast, therefore, is much better. So the objectives for today, we're going to talk about radiographic grids, why we would use them. We'll talk about the actual manufacture and physical and functional characteristics of a grid. We'll move into grids that are able to move as per a Bucky device. And we'll talk about why they would move, the rationale. We'll talk a little bit about some mechanisms and limitations of grids. We'll get into the principles and what we will need to do in terms of adjusting our exposure factors. We'll continue on to grid cutoff, which is an issue when grids are not used properly. And then we'll talk about an alternative to using a grid, which is known as an air gap technique. And we'll talk about why that is used occasionally and some of its applications/limitations. Later on, near the end of the lecture, when I get to grid cutoff, I'll move to an additional document where there are a few more slides. I'll also post that on Blackboard for you. So last week, we talked about one way to reduce scattered radiation, and that was via beam limitation. That was the use of, namely, a collimator. That was the use of an aperture diaphragm, all of them to basically cut out the edges and shape the beam geometry. Now, in those cases, we can remove some of the scatter and improve contrast. And there is no harmful effect at all to the patient. As a matter of fact, if you collimate, in other words, reduce the the field size, then you will have basically less photons interacting with the skin and then less dose to the patient. A problem occurs, though, if the body part is too thick. So when we say thick, we're talking about 10 centimeters or higher. Okay, in a situation like that, we are required to use much more exposure technique, certainly much more KV. So generally speaking, for extremities, we don't need to use a grid, right? They're small objects that don't require a lot of exposure. But when we get to larger body parts, like a shoulder, like the lumbar spine, skull work, shoulders, then we're going to need a grid. And for me, the part that is pivotal is a knee. If we have a fat knee or a large knee, you might be better off getting a better image by utilizing a grid. Other than that, you can do tabletop. So for a knee, it can kind of go either way. So if we are going to do a large part, let's say a KUB or a chest, we're going to want to use a grid. Now this grid is placed between the patient and the image receptor. So in other words, you have your beam that interacts with the patient. Some of that radiation is going to come out of the patient. That is known as the remnant beam. A lot of what comes out of the patient is going to be scatter. This is what we are going to try to get rid of. By placing a grid after the patient but prior to the image receptor, the attempt is to remove the scatter before it interacts with your image receptor, be that a film or a CR cassette or a digital detector. So basically, it's going to help remove scatter, right, but allow transmitted photons to reach the film. So we're going to discuss in a few minutes the makeup of the grid, because it has to be designed in such a way that certain photons, the ones that are deflected and Compton scatter, are destroyed, while transmitted photons that are going nice and straight can go through and have an impact with the image receptor. So the amount of scatter that is reduced is going to be dependent on several things, right? One is the angle of the scattered photon. Depending on that angle, the grid may or may not absorb that scatter. The other dependency is the height of the grid strips compared to the third bullet, the width of the interspace material. So the height of the grid strips compared to the width of the interspace material. That is known as the grid ratio. So the idea is that our grid will improve radiographic contrast. Again, we're going to absorb some of the scattered radiation before it actually interacts with the image receptor. So here is our patient. Our radiation goes through the patient, interacts with the grid, and some of the rays, some of the photons, are allowed to go through while others are not. Again, our consideration for using a grid is based on the part thickness. The thicker the part, the more exposure technique we need to use, especially KV, the more scatter we will be creating. So really we should consider using a grid when we are above 60 kV and or above 10 centimeters in part thickness. And we can put a numerical value on contrast. And we can talk about what's known as contrast improvement factor. Contrast improvement factor, or known as K, really indicates the ability of a grid to improve image contrast. What I want you to remember, the bottom line really, is that most grids have between 1.5 to 2.5 grid improvement factor, or CIF, right, which is approximately double what you would have in terms of CIF contrast without a grid at all. This is generally measured at 100 kVp. So our formula for contrast improvement factor is simply the image contrast with a grid over the image contrast without a grid. So for example, this is an example where we have a radiograph of a part that measures 20 centimeters, certainly worthy of using a grid. It is measured at having 1.1, what's known as average gradient. We will be dividing that into 2.8, okay, and getting a grid factor of 2.55. So to refresh your memories and to go back, the image contrast with a grid compared to the image contrast without a grid. Higher numbers, better contrast. So here is our contrast improvement factor once more. These are factors that would be given to you on an exam. So our goal, again, to reduce scatter, right? And to refresh your memory, scatter really deteriorates the image. Scatter lays down unwanted densities on the film. It also appears, by the way, in digital imaging, except we wouldn't refer to it as a film, but it adds unwanted brightness or darkness to areas. Basically, it destroys the visibility of detail. So the detail is there. However, when you overlay that detail with scattered radiation, it becomes much harder to visualize. Removing scatter will improve contrast. That will then allow us to visualize the detail. So what is it that makes a grid work? Well, a grid consists of very thin strips of lead, little lead lines, separated by a radiolucent material such as plastic or aluminum. In other words, there are lines and spaces between the lines. A photon interacting with any of these lead lines would be destroyed before hitting the image receptor. Thus, that scatter would not end up on your image receptor, and you would improve contrast. Right, so we have a lot of lines. And grids are very hard to manufacture because when it comes to what's known as grid frequency, how many lines you may have per centimeter or per inch, those numbers get into the low hundreds. So we're talking about very, very thin lines. But then again, how big are photons, right? Depending on that interspace material's width, some photons will just fly on through with no problem. Others, if they interact with one of the lead lines, again, they will be destroyed and will thus not allow that scatter to be represented on your image. So most of the transmitted photons pass between the lead strips, but a lot of them, the scattered ones, are going to be stopped by the lead because they are traveling at an angle, right? So if we remember, you have your X-ray source, you have your part, and after, in that remnant beam, you have some photons that are going to come through, and even though this is at an angle, this green line here, it still is transmitted. However, these photons represented by the two red arrows, they are at an angle, so their deflection creates a situation where they will interact with a lead line and be destroyed. A grid is very good at cleaning scatter. We'll talk about the trade-offs because a theme of this course, as you've seen, is in many cases, anytime when something good sort of happens, there's a downside. So a grid will remove anywhere between 80% to 90% of the scattered radiation. which is a significant amount of your total amount of radiation to begin with. Keep that in mind because we are going to have to discuss what to do when we reduce the amount of radiation coming out of the body and we may not have enough radiation to actually create an image. So grids from the outside really only differ in their size and shape. So there are grids that are 10 by 12 and grids that are larger, such as 1417. We've seen some of these grids in the laboratory. We can slip the cassette right into the grid. But when we speak about grids, we want to get more particular, right? And we want to talk about grids from two factors, really, two types. There is a focused grid, and then there is a linear grid. So linear grids are grids that have their lead strips that run in only one direction. So if we take a cassette, like a 1417, and we hold it in front of us so that the long side is going from our left hand to our right hand, imagine many, many lines going through that cassette, or that grid, excuse me. The advantage here is that our central ray can be angled along those lines. What cannot happen, though, right, if you go against the long axis of the lead strips and angle towards any of those lead lines, then we would be pointing photons directly at a line. They would then be absorbed, and our percentage of scatter being absorbed along with transmitted photons would increase, leading us to an incredible loss of density. Right? This is one type of what's known as grid cutoff. So we're going to talk about some of the details about what makes one grid different from another that go beyond merely just the size of the grid. So again, we can break grids down into what's known as a focused or a linear grid. So when it comes to linear grids, right, we have what's known as a focused linear grid versus I know it sounds a little strange, but a linear grid. And I'll explain the subtle differences in a second. But a focused linear grid will have lead strips that are tilted, okay, versus parallel. They're tilted so that they are parallel to the diverging beam. So if you take a look at this image over here, right, you can see that our beam is diverging, and if we look at these little lead lines down here, these boxes at the bottom, are they parallel? No, they are focused and parallel in line with the beam as it comes down. So the idea is if you are utilizing a specified focal distance, so what I mean is that it's important when using a focus grid to be within the directed focal distance. In other words, SID. Focus grids are made with generally either a 40-inch or a 72-inch focal distance, which means if you are doing, let's say, a portable examination up on the floor, patient is in the bed, you have your portable machine and you have your grid. If you are less than 40 inches, then you are not within the focal distance of a focused grid, and you may have what's known as grid cutoff, right, or unequal density that even in the CR environment cannot be fixed. Also, these grids are designed to have a front, which is known as the tube side, because you can also have drastic results if you have the grid upside down, and I'll show you what some of those images look like a little bit later. So the X-ray grids are available in a variety or variable ranges of focal distance. And when it comes to what's known as grid ratio, that allows us for a much wider latitude in taking our image. So let me explain this to you for a moment. When we talk about grid ratio, we are talking about the distance of the lead lines, the length of the lead lines, compared to the width of the interspaced material. So we are basically talking about how big is the space between any of the two lead lines. When the grid ratio is increased, so if we go from, for example, a 10-to-1 grid to a 16-to-1 grid, the higher that grid ratio, the smaller the space. So what that means is the ability to move your tube around, especially when doing, let's say, a portable exam, is limited when you have a very high ratio grid. You have to be much more exact. It is much less forgiving compared to using a smaller grid ratio, let's say a 10-to-1 grid ratio. The actual width between any of the two lead lines is much wider, which means if we are off a little bit in terms of our angle and in terms of our SID, a lot of our photons will still make it through and get to the image receptor. The trade-off, however, is a higher grid ratio will clean up more scatter and thus increase contrast. So lower the grid ratio, worse the contrast, not as much cleanup. Higher grid ratio, much more scatter cleanup, and a better result or increased image contrast. So to sum things up, if you're not sure what your SID is, okay, some of the portable machines aren't very good at giving you what your SID is. They might have a tape measure, but because you're at an angle or your image receptor is underneath the patient, it's kind of hard to figure out where you are. You would want to use a lower grid ratio, which would give you more latitude in terms of positioning. Less likely to have, again, what's known as grid cutoff, right? Which is a problem when we are out of focal range or when we do any number of things with the grid that you're not supposed to, like having it upside down or being off center. I'm jumping ahead, so we will talk a little bit about some of those issues that can occur. Some of the focal distances available you have broken up into small, medium, and large, 26 to 32 inches. That's definitely not very useful for us. Most of the exams that we do take place between 40 and 72. So really, we would like to use a long focal distance, somewhere between 40 and 72. The problem there is, again, it is possible to be a little bit less than your normal SID. Let's say you're at 36 or 34, and then you would have a problem with your grid. Another term I want to point out to you, when we talk about this focal distance, it's kind of like SID. The point that we are actually measuring is from the tube, from the source, or what's known as the focal point, to the image receptor, right down here. Now, when it comes to what's known as parallel linear grids, so also known as linear grids, in this use, it doesn't matter where the tube is located, right? We're never going to have any kind of condition where the strips need to be lined up. In other words, now, compared to our last image, we have little squares here, right? And if you notice, they are all parallel with each other. So this can be used at most SIDs, most focal distances, other than it is not recommended to use a parallel grid at any distance that is less than 56 inches. So this would not be utilized in a table Bucky, for example. Why is that? Our table Buckies, most of our Bucky work or non-table work is done at 40 inches. So a parallel grid would not work for this. However, in practice, a large SID, no matter what the divergence of the beam, we would not have a problem with a parallel grid. So we could have basically an infinite distance in SID. Now a cross-hatch grid is really also known as a crisscross grid, and it's basically two parallel grids that are at 90-degree angles from each other, so they create basically a checkerboard. Now, in this case, because you create squares, a checkerboard, any possible way that you angle the tube is going to angle those photons into a lead line. So you cannot use, and I repeat, you cannot use a cross-hatch grid if you plan on angling the tube. Right? Remember, with the linear grids, as long as you are angling in the same direction that the lead lines are running through the grid, you may angle. Crosshatch, you cannot. So a crosshatch grid, though, will give you very, very good scatter cleanup, because essentially it's two grids, but you are very limited in your positioning. Okay? If the tube is angled, or if the grid is angled, in other words, the grid that might be right underneath the patient, who is in a bed not on a hard surface, very possible for that grid to tilt underneath the patient. Cross grids, we have some in the lab, and we will practice using some of them, but they are, in practice, very limited in terms of latitude with which to move your tube around. They would be very low, very difficult to use. However, if used correctly under the correct circumstances, they would provide a very good scatter cleanup and then thus very high contrast. So we've been using this term grid ratio before, right? There are two major indicators of a grid's ability to remove scatter from the exiting beam, the remnant beam. And the most useful one is what's known as the grid ratio, right? So our grid ratio is the height of the lead strips compared to the distance between them. So here's a lead strip. It's the height divided by the distance between them. So grid ratio is equal to H over D. And as we've mentioned, some of the grid ratios that are common are a 5-to-1, 6-to-1, 8-to-1, 10-to-1, 12-to-1, and 16-to-1. Remember, higher grid ratios, better cleanup, right? If this space here, this distance, gets smaller and smaller and smaller, that would be indicative of the grid ratio increasing. And for the record, it's always X to 1, 5-to-1, 10-to-1. It's always something to 1. So again, grid ratio is simply the height of the lead strip over divided by the distance between the strips. So as mentioned, a higher ratio grid is going to be more efficient. It's going to be better at removing scatter than a lower grid ratio. So contrast improvement is going to be greater with a higher ratio grid. Higher ratio grids would also be utilized if you're going to use higher KV. Higher KV, more scatter. The more scatter that you intend to create by no fault of your own, the patient being large or the object being large requires an increase in exposure, the more you might think about using a higher grid ratio. So here's an example of grid ratio. If a grid had an interspace material of 0.5 millimeters, so that's pretty small, by the way, right? Half of 1 millimeter. That's really barely putting your two fingers together. Okay. What would be the lead strips that are 3 millimeters high? What is the grid ratio? So simply it would be 3 millimeters, right? The height divided by the interspace material, right? The distance between those lead lines being 0.5 gives you a grid ratio of 6:1. There's another term known as the grid factor, right? The grid factor describes the fact that many more photons are interacting with the grid than can make it through the grid, right? The grid factor measures the primary and scattered radiation through the grid. So we have our incident X-rays over our transmitted image and our forming X-rays. There is an aspect of dose in here. Basically, what I want you to understand is a grid does too good of a job. And because not only are the deflected Compton scattered photons destroyed, but many of the what would be useful photons that would normally be transmitted and provide good contrast and image information are also destroyed. So we are going to need, based on our grid ratio, to alter the exposure technique. In other words, we are going to have to increase our exposure, and particularly we're going to increase our exposure higher and higher as grid ratio increases. So there is a price to be paid to the patient in terms of dose. And we're not talking about a little bit of dose. We are talking about 4, 5, 6 times the dose, depending on the grid ratio utilized. Multiply that by multiple views, and you'll see how things start to add up. So when it comes to grid factors, if you look at this chart on the left, you'll see that there are a series of columns and a series of rows. Up at the top, in terms of columns, we have a 70, 90, 120, and average KVP. I want to focus on the average KVP. What we have in terms of rows are what the grid factor would be if there is no grid, what the grid factor would be if you have a 5:1, an 8:1, a 12:1, or a 16:1 grid ratio. And as you can see, these numbers go up as the grid ratio goes up. Let's take a look at an 8:1 grid. If we have an 8:1 grid, we are going to have to multiply our exposure 4 times what we would have used with no grid. If we use a 12:1 grid, now we are going to multiply by 5. So patient dose and radiographic technique increase proportionally by what's known as the Bucky factor. Really, the Bucky factor is only telling us what we need to do to our mass, to our quantity of radiation. How much are we going to increase? The higher the grid ratio, the higher the Bucky factor. In other words, a higher grid ratio requires a larger amount of radiation. And technically, if you use higher KV, you would also require more radiation. All right, so as we go from, if we look at an 8 to 1, at 70 kVp requires 3 times your amount of radiation, 90, 3.5, 120, 4. So again, what you are going to have to memorize is the grid ratio and the average change or average grid Bucky factor. So different grids have a lot of different properties, with some cutting out more scattered radiation, but as I've mentioned, also blocking out these useful X-rays. So this is where our Bucky factor comes in. We're going to have to increase our exposure if we go to a higher grid ratio. There is another factor, though, and that is known as grid frequency. Grid frequency is based on the number of lead lines, per inch. Sometimes this is measured as per centimeter. So it is possible for your grid ratio to remain the same. In other words, you may have 2 10 to 1 grids, but they may have different numbers of lines per inch. In other words, how many lead lines there are. Grid frequency plays a role in scatter reduction, and also can be detrimental to the image in that if you have a low frequency grid, not that many lines, those lines can show up on the image and be distracting to the radiologist or whomever is reading the image. So grid frequency, again, is just the number of lead strips, PB for lead, per centimeter or per inch. If we increase the frequency, we are going to make the interspace material less and less, right? So if you look at these examples here, both of these are 10 to 1 grid ratios, but here, what's changing is the actual thickness of the line, right? So that we can have more or less lines per inch. A higher frequency grid, one such grid that has many lines, will be a lot better at removing those grid lines from the final image. In other words, lower frequency will possibly show lead lines on an image. Higher frequencies, less likely. And in general, the frequencies vary from 103 to 200 lines per inch, right? So that's 103 to 200, or 41 to 80 lines per centimeter. Of course, centimeters are smaller, so these two numbers are proportional to each other. We're going to talk again a little bit about grid frequency when it comes to the use of a Bucky. But that's a little bit down the line. Or, excuse me, right now. So, I'm not going to give you too much of a history lesson. But back in the 1920s, there was a gentleman named Hollis E. Potter. And he realized that if we took a grid and moved the grid, or had it reciprocate, another term is oscillate that grid, that if this occurred during the exposure, we could blur those lines out. So essentially the grid lines would disappear. So he created a device known as a Potter-Bucky diaphragm, right, to do just that. This Bucky device would take the grid that was built into it, utilize a motor that would go back and forth several times during the exposure, right? At one time, you used to have to crank this grid up and kind of twist something, similar to the way you might have one of those little toy cars and you would move it back before letting it go and having it go forward. Now, the reciprocation of the grid is built into the system and occurs during the exposure. Starts when you are using the rotor prior to hitting the exposure button, and then lasts during the duration. I did see a YouTube video that I'll try to post for you that shows the grid moving back and forth within the Bucky device. So again, it's going to be necessary that when the grid ratio changes, that we either increase the mass or increase the kV. I am going to focus on increasing the mass, increasing the quantity. So when it comes to a grid, if there's no grid, well then there is no Bucky factor really. We are just going to multiply the initial MAS by 1, which gives you the same MAS you started with. So this is really a factor of what to do when you change from no grid to a grid. So if we started with, let's say, 10 mass, and we now are going to an 8-to-1 grid, you would be required to multiply that 10 mass by 4, giving you 40 mass. Alternatively, you could increase your kV by 13 to 15. But for exam purposes, I want you to focus in on just these numbers here. What you need to do to your mass versus what you would have to do to your kV. And as you can see, at a 16-to-1 grid, you can possibly go from, if you started with 10 mass, now you find yourself going to 60 mass, right? That is a large increase in the dose to the patient. So, for example, when going from a non-grid to a grid, it's fairly easy. If your mass is 15 without a grid, and now you switch to an 8-to-1, what will your new mass be? Well, this is where you have to remember your grid factors. You have to know that an 8-to-1 requires a 4 times increase in mass. So that would say 15 times 4 would give us 60 mass. Now, what if you already have a grid of a certain grid ratio and you want to switch to another grid? Then we need to use a formula. It's not as simple as multiplying our initial mass by 2, 3, or 4, right? In this case, we have to do a conversion where first we have our first mass at our first grid conversion factor, and we want to know, what our second mass will be if we switch to a new grid. So for example, in this case, an image is produced using an 8-to-1 grid. Right? An 8-to-1 grid has a grid conversion factor of 4. So that goes here. And initially we're using that grid at 20 mass. That is our first mass. What would the second image require in terms of mass if we now are requested to use a 16-to-1 grid? So X goes here for what our new mass would be, and our grid conversion factor for the second grid, that being the 16-to-1, is now 6. By the way, the rationale here is that we are needing to increase contrast. That would be the only reason to go from a lower grid ratio to a higher grid ratio. And that being the case is going to require us to use 30 mass instead of our initial 20 mass. Right? This is not as huge a number as we saw in the previous examples, because in the previous examples we were going from no grid to a grid. In this case, we started with one grid and moved to a higher grid ratio. Now, I want to talk a little bit about some of the problems that you can have with a grid. they are not the easiest devices to utilize. Right? It's very important that you have proper alignment between the X-ray tube and the grid. If the grid is, for example, off center, right, or off level, meaning it's tilted, right, at an angle, or if it's off focus, meaning that your central ray is not centered to the center of the grid, or, and this really shouldn't happen, if you use your grid upside down. As well, there are some issues when you utilize a grid combined with a CR, computed radiography system. You can have what's known as the Moire effect, M-O-I-R-E. Right? All of these are going to cause serious problems with your density. So I'm going to switch to another PowerPoint that I have, or example. Or at least I'm going to try. Okay, so I'm going to run you through this. This is a PDF that I found. Has some good information on grid cutoff. And as you can see, a decrease in the number of transmitted photons that reach the image receptor is what's going to cause grid cutoff, right? And as mentioned, some of the errors that we can have would be an off level, or an off center, or an off focus grid, or the grid upside down. So I thought I'd run you through some of these. So here's an example of an off level grid, right? That is going to create a decreased density across the entire image, right? Because essentially now we are going to have photons that are inadvertently going to hit more lead lines than they're supposed to. In other words, we will be annihilating a lot of those good photons that would have been transmitted. Sorry about that. How about off center? Now, when you are using what's known as a focused grid, a focused linear grid, you can see that our lines here, like these two, are not parallel. A focus grid is designed to be used, again, within a certain focal distance, so that the lines and those spaces between the lines match up with the divergence of the beam. If we are off center, right, in other words, our central ray here is now a little bit to the left compared to the proper position over here, that is going to create a situation where the divergence of the beam no longer matches up with the slightly different focused lines and spaces. This happens all the time and is very easy to happen when using what's known as a stationary grid. When you use a stationary grid on a portable exam, right, that grid is going to go underneath the patient, and then it's very hard to know where the center of your grid is. Whereas if you use the grid that is built into the Bucky, we have a lot better control because that tube will be detanted or transversely locked into place so that we know the central ray is going through the center of the Bucky and the center of that grid. So if we had a choice and we have to use a grid, we would want to use a grid that is in the Bucky with the patient on the table versus going up to a patient's floor and doing a portable study. Of course, a portable study should be ordered only if a patient cannot make it to the department. Okay, here's an example of an off-focus grid. We're, in this case, going to have decreased density at the edges of the image, right? And this is more of a problem if we have a grid ratio that is high. Right? In this case, we are outside of the proper SID, the proper focal range. Down here, we have an upside down grid. Right? Here, with a focus grid, remember our lines are matching up with the divergence of the beam. However, if it is upside down, we are basically going to have a huge decrease in density at the edges and all of our density in the middle of the image. Right? So please don't use the grids upside down. This is something that certainly cannot be fixed with our CR or DR systems. Okay, a little bit of more information. An upside down grid would not be an issue if it was a linear parallel grid, because then it wouldn't matter. The interspace between the lines would stay the same whether you were upside down or not. So here's an example of some grid cutoff where you are off level. Right? See, we have a huge decrease in density across the image. Again, we have grid cutoff here because we are off center. Right? This point here, our focal point, is now going towards the left side of the grid versus being in the middle. Here is an off focus grid, so we are outside of our focal distance. Again, we have a general loss of density. And our upside down grid, one of my favorites because it's very evident that you have an increased density in the middle, where towards the periphery, as you can see here, a lot of the photons are getting destroyed at the periphery of the grid, yet they go through the middle. That's the way the focused grid is designed, generally for the divergence of the beam. But if you flip that around, everything is reversed. I'm going to go back to the PowerPoint. And I want to talk very briefly about another technique known as the air gap. I like to call this the poor man's grid because instead of utilizing the grid, we are going to create a gap, basically OID, object image distance, between the part and the image receptor, such that we have about 10 to 15 centimeters between the patient and the image receptor. The idea is that the scattered radiation that's in the remnant beam, the beam that comes out of the patient, will die in the air. Photons will essentially die in the air or kind of split off so that only the ones in the middle make it to the image receptor. So in this case, we have to increase our exposure. So we still have to increase exposure to the patient, right? Approximately 10% for every centimeter, right? And it is occasionally used in chest radiography or cerebral angiography. I personally have not used the air gap before. There are some issues with air gap in that if you were to use this multiple times on the same patient, the level of magnification would most likely be different each time. So to try to keep things consistent, using an air gap is very difficult. As well as because we have magnification, we're going to lose some of the detail. Right? We do increase our SID to try to make up some of that. In other words, a longer SID reduces magnification, right, and minimize the image to counteract the OID, but it's still not really enough. We will do this in the lab. I did do this with some of you, and I'll try to make sure that everyone sees this at least once. Right, so it is much less expensive than the grid, and I wanted to end with a little bit of the economics of a grid, right? So on the next slide here, you can see that these grids are quite expensive. So you can imagine that a lot of craftsmanship has to go into making sure that you can fit 100 lines within an inch. Right? Imagine trying to draw 2 lines on a sheet of paper and then 100 other lines between them with a small little space in between. Very difficult. So please don't drop the grids. So to sum up, in summary, the grids do nothing for patient dose compared to beam limitation devices, which can lower patient dose. Grids will improve contrast, so they are only good for image resolution, not for the patient. Grids vary in their size, but more importantly, they vary in their grid ratio, which is the height of the lead line divided by the distance between them, such that higher grid ratios have a smaller space between the lines and will thus annihilate more photons, leading to better contrast. Conversely, lower grid ratios have a larger space between the lines, which allow for more positioning latitude. But the trade-off is they don't clean up scatter as well. So I hope you found that interesting. Unfortunately, we need to use grids despite the fact that we are increasing the dose to the patient. If you have any questions about this lecture, please feel free to email me. I thank you for your time.